Welcome to ePadasala PG program for computer science students. Today we will be looking at embedded C program for timers. So in this module we will be discussing about accessing the timer registers and how to calculate delay for fixing up using timers, and we will be discussing about embedded C programs for timer and counters. So when you are looking at 8051, we know that we have two 16-bit timers. It can be used as counters also. When you are looking at these two timers, we will call this as timer 0 and timer 1. These can be configured independently to operate in a variety of modes as timer or as counter. So when operating as a counter, it has to be set, and if it is a timer, it has to be set as 0. So when you are looking at to setting up whether it is a timer or a counter, we need some register or control bit to identify whether it is a timer or counter. So when you are looking at an timer, we will be having either 16-bit length or 8-bit length, or maybe it is configured to 13-bit also. So when you are looking at a counter, it can count whenever it is getting a negative transition on the external pin. So each and every time it gets a negative transition, it counts it, so that if I am making it for 1 second, then the frequency of occurrence of the inputs at the external pins can be counted and it can be displayed. So when you are looking at this timer operation, we have two registers which will help us to make use of this timer. One is your TH register, another one is your TL register, where because we have two timers, so we will have TX0, TL0 combined together for timer 0 operation. If it is TX1 or TL1 combined together to make it for timer 1 operation. So we have a TRX bit, maybe I will say that TR0 or TR1, which will be available in your TCON register, which turns the timer on. By making it becomes 1. So when it becomes 1, each time the timer increments. If it has been set it into timer mode, then the timer increments by 1 with your TLX. If it overflows, the THX gets incremented. So if both the things are getting overflow, then the overflow flag TF is set as 1 in TCON register. So this setting up the TR bit will make the timer to start run. So timer 0 or timer 1, when you are having TMOD register where there are two bits M1 and M0 which are combined together to make operating modes. So maybe four kinds of operating modes we can set it, but usually we will be looking at timer mode 1 and timer mode 2. These two are very famous things. If it is 1, it may be for 16-bit operation. 16-bit timer can be used with that, and if it is set as 2, then it is a 8-bit timer mode where it is a auto reload also. So those things we covered in the previous lessons also. But anyway, when you are looking at the embedded C operations, we need to know what are all the controls we need to set before writing a code onto the C. So modes, when you are looking at a timer or counter, both the things needs the mode has to be set. So when you are looking at the registers, the control registers, which are all TMOD and TCON, these two are control registers, whereas TH and TL are meant for timer register. So TMOD is used to select the mode of operation, TCON is used to control the timer to run either stop or start. When you are looking at TL and TH, to hold the data, so that we will find out how much is the delay we have generated over there, as well as we can put a particular value in these registers to make it how much is the delay we need to generate. So TMOD is 8-bit register where the lower 4 bits for timer 0, whereas the upper 4 bits are for timer 1. The lower 2 bits are used to set the timer mode in TMOD. So the upper 2 bits specify the operation with your register. This shows that TCON registers configuration. So you just see that these are all, this TF1 is a overflow flag if for timer 1. If it gets overflowed, then this will be set as 1. TR1 is nothing but timer control bit for timer 1. TF0 for timer 0 overflow flag. TR0 is for timer 0's run control bit. The lower nibble is meant for interrupt based communication. So, when you are looking at this IE1 is interrupt 1 edge flag, IT1 is interrupt 1 type control bit. This has been set so that interrupt is a edge kind or normal kind, that means the external input has been, when we are using it as a external interrupt. So, by the time these bits are very useful. So, that when you are looking at, these are the 4 things which we will be looking very important when you are operating in the timer mode. So, now we will be looking at how to generate a delay. So, first thing is we need to make the TMOD has to set with the values, then the TL and TH has to be loaded with what will be the delay we need to encounter, then we have to start the timer. Then we will be looking at whether the timer flag is set or not. When it is set, then we have to come out from the loop. So, this is the way we will be generating a delay with the use of the timer. So, once the TF flag is set, then we will find out that the exact delay has been encountered. So, stop the timer and clear the TF flag, and if we need to generate again the same delay, then go for the next round. So, this is the way, then go back to step 2 to load your TH and TL again. So, this is the way, maybe this is for making it iteratively, you need to generate a different, the same delay continuously. So, for that particular reason, we have to follow this kind of operations. This is the steps to be followed. So, when you are looking at timer 0 and 1 in 8051, see all these basic things we have seen for the timer 0 and timer 1, we need to know, so that we will be writing a code in 8051C, that means embedded C. So, when you are looking at embedded C, where the general purpose registers such as your A, B accumulator, B register and R0 to R7 general purpose registers, all those things are under the control of C compiler. So, you can't access it directly, these registers. And when you are looking at something like the SFRs, so this space, RAM space is accessible directly using the 8051 C statements. It is just like we will be writing a code in high level language for this 8051. So, that way only we have to encounter it. So, this is an example program where we will be writing a code, embedded C code, to toggle all the bits of your port 1 continuously with some delay in between. So, we will be using the timer 0 16-bit mode to generate the delay. So, in this you just see that we have included, as like the previous modules we have come through, in embedded C program we have to include reg51.h. So, this says that the code has to be written for 8051 controller. So, because of that it will be converted into that instruction set. So, now this is the routine we will be using for generating a delay. So, subroutine is declared first, then the main is declared. Now, while 1, so this is for generating an indefinite loop, while 1 is generating an indefinite loop. So, in this P1 is equal to 0x55. So, now I will be 55 is telling you that 10 10 10. So, that way it has been written, and there is a delay is called. After that your P1 is equal to AA. So, what it means is 0101, that means I am toggling, if I am putting it 1010, next time it is 0101. So, that means I am toggling the LEDs with a small delay, this has been called, and the LEDs are connected at P1. So, remember that in embedded C you can call the ports directly. So, P1 these are all the ports you can access directly. If I am making use of P1, it says that port 1. So, the port 1 is equal to 0x55, in the sense this value is moved to this particular LEDs which are connected in series, connected parallelly in your P1 port. So, now this delay is generated using your timer. So, how we will be generating it, that we will see. So, in the TD delay we made TMOD is equal to 0 1. So, it says that 0 1 in the sense the second half is 1. So, because of that it is timer 0, it has been declared as timer 0 and mode 1, and TL0 is 0 0, TH is 35. So, why we have set TH is, now you just see that if I am making it, it is a timer mode 1, then it can run up to 16 bits. So, if I am saying that the overflow will occur when you are getting one FFFF. So, after that only if it increments it goes to overflow. So, the maximum count is 4 Fs. So, minus 3500H is nothing but CAFFH. So, the CAFFH is nothing but when you are converting it to a decimal number, which is nothing but 51,967 is the number timer it has to, if I am loading it this value, the timer has to count up this many numbers. So, plus 1 because I am subtracting it, because of that it is plus 1. So, 51,968 is the timer count, we are making it as a delay. That means how much is the time we will be generating as a delay is nothing but, because it is nothing but this particular oscillator is looking at 11.0592 megahertz oscillator. So, each machine cycle takes 1.085 microsecond. So, timer counts for 51,968 time into 1.0085 microsecond. 1.085 microseconds multiplied with this will gives you 56 milliseconds. So, if I am loading this particular value 3500, if I am loading it TH with 35 and TL with 00, which counts up to FFF, which in turn makes a delay of CAFF, which is nothing but 51,968 timer count. So, that is the delay it encounters if I am putting this as the initial count. So, these are the initial counts we made it. After that we made it TR0 is equal to 1. That means we have started the timer. So, now I will be making it while TF0 is equal to 0. If I am looking at TF0 is equal to 0, so till then that particular condition it is going in a loop. Once I am getting a TF0 is equal to 1, from the loop it comes out. If it once TF0 is equal to 1, then it comes down there, TR0 is equal to 0, TF0 is equal to 0. So, this stops the timer as well as the overflow flag also cleared. So, which makes the time delay is generated, if I call this time delay, which generated 56 milliseconds, so that the P1 is existing in 0x55, that means 1010, that way the input is given. So, after this delay I will be calling again 0xAA. So, AA in the sense maybe 1010. So, the LEDs are getting toggled, so that in between the delay generated is 56 milliseconds. So, now when you are looking at this calculation, you just see that we have to, when you wanted to make, this is the delay has to be generated in between two operations, then we have to divide the desired time delay by 1.085 microseconds, then perform 65,536 minus this particular desired time delay. I mean what will be the number we got it in the first step, whereas n is the decimal value we got it in step 1. Then convert that particular result into a hex code, which is loaded to TL and TH. So, by loading these value and we start the timer, we will wait till TF is equal to 1, then we will be generating that kind of delay. So, remember that this 1.0885 microsecond is for 11.095 megahertz. 952 megahertz. If it is 12 megahertz oscillator, then 1 microseconds. That way, what will be the crystal oscillator, we are looking at the CPU clock cycle generation. Based on that only we have to take what will be the clock cycle. So, the machine cycle time, based on that what will be the initial count we need to load it also will get changed based on this particular value. So, when you are looking at the timer 0 or 1, so delay when you wanted to use mode 1, 16-bit non-auto reload, if I wanted to do it, this is an example program. You just see that, write an 8051C program to toggle the bit P1.5 continuously for every 50 milliseconds. So, use timer 0 mode 1 to create the delay. So, now test the program on 8051 controller. So, in this if this is the case, that means I am just toggling only the pin P1.5 with the delay of 50 milliseconds. So, the LED is already connected over there. So, now include reg51.h which says that it is for 8051. This header file has to be included, so that the whole thing is converted into 8051 machine language when you are compiling and using it for your machine language. So, void tmod delay, tmod 1 delay is the subroutine we called for generating a delay, and I am setting it s bit of my bit which is p 1.5. Now, I am writing my main code void main void, where while 1 is nothing but indefinite delay I am creating it. My bit is equal to inversion of my bit. That means I am toggling it, my bit's inversion is equal to my bit. That means first time if it is 1, then it becomes 0. So, if I am putting a 0 over there, then it becomes 1. That means I am just complementing or inverting the bit which is in the my bit. That my bit is nothing but p 1.5 bit. So, now I am just doing this toggling. After that, the delay is called. If I am calling this particular delay, so how much is the delay I have used? So, I have been asked to generate a delay of 50 milliseconds. So, if it is 50 milliseconds, then I need to go ahead with FFF minus 4B, FD is nothing but B402H, which is nothing but 46,082 plus 1, which is equal to 46,083 is the timer count I can generate. So, now if it is multiplied with 1.085, then it is 50 milliseconds. So, I need to load the value of 4B FD to my TL and TH together, so that I can generate a 50 millisecond delay. So, just see that tmod 0x101, so it is timer 0 mode 1 is set, TL0 is FD. So, you just see that the TL is loaded with the lower byte, TH0 which is loaded with the 4B. So, now TR0 is equal to 1 is set, so which in turn starts the timer. Now, I have to wait till the TF0 is equal to 1. For that I am writing an indefinite loop while TF0 is equal to 0. If it is equal to 1, it comes down, TR0 is 0 and TF0 is 0. So, that I am just resetting it, so that I will be coming back. So, because this thing is over by up to this, so that we will say that it gets returned back. So, that each and every time I am encountering a delay, it comes over here, after that it gets inverted, again it goes there. So, the inversion takes care about toggling the bit at P 1.5. The next example we will be looking at is to create a delay of 500 milliseconds, so that the toggle all the bits of P2 for every 500 millisecond using timer mode, timer 1 and mode 1. So, you just see that it is very simple, the same way what we have done it with the timer 0, the same way here also we made it void time 1 delay. Here unsigned character X. Now, P2 is equal to 0.55 while 1. Now, P2 is inverted, that means whatever be the port values which is getting inverted and placed at again the P2, and we called the time delay 20 times. So, that means when you are looking at smaller values, we need to execute it with only one time the delay is called, but if I am looking at the delay is of more, maybe 500 milliseconds, then I cannot run it with just only one time the timer has to be loaded. So, if I need a more delay, it cannot handle in a single iteration, then I have to make it within a for loop. It will be called for 20 times. So, 0 to 20 times the time delay is called, so that it has been achieved to get this particular 500 millisecond. You just see that the same kind of thing we have done it over here, but the delay is called for 20 times. So, you just see that 20 into 25 millisecond is 500 millisecond, where 25 millisecond is generated with 23,042 multiplied with 1.085 microseconds. That means one delay 23,042 is generated with by loading this particular value with your thing. So, remember, with only one time execution 500 milliseconds cannot be got. So, because of that only we have called this delay for 20 times, which in turn generates 500 milliseconds delay. And you just see that this is loaded. So, these values are loaded, TR1 is equal to 1, TF1 we will be waiting, TF1 is equal to 1. When it is 1, it comes over here, it resets. Again it goes over there, the x is getting incremented, again we call the delay. The same way the for loop is getting executed for 20 times. So, because of that the 25 seconds delay generation, this loop is called for 20 times, which in turn makes half a second, that means 500 milliseconds. By using it for half a second, I need to run this timer for 20 times to generate this kind of delay. So, now you just see that we have till then we have gone through only the mode 1. Now, we will going this mode 2 timer 0, using this particular mode we will be in a position to generate a delay, so that we will be achieving a particular application. So, this is an example where write an 8051C program to toggle the pin P1.5 continuously every 250 millisecond using timer 0 mode 2. That means 8-bit auto reload that to create the delay. You just see that I have made it, this is a timer mode 2 delay, this subroutine we have declared first, then my bit P1.5 S bit, yes, I have declared S bit as my bit P1.5, then with the main the character X, unsigned character X and Y is declared, while 1 my bit is equal to inversion of my bit, that means complement of my bit. I am inverting it because we wanted to toggle it. So, now for X is equal to ranging from 0 to 250 and Y is ranging from 0 to 36, put together we will be making the delay of T mod 2. So, this has been called nested loop of 250 into 36 of this particular number. You just see that 250 into 40 is the number of times the loop is rotated, and 25 microsecond each time 25 microsecond is generated. For generating it, that gives you 250 milliseconds. Because it is a timer mode 2, so only 8 bit is there, so we can have only a lesser value has to be loaded. So, because of that 256 minus 23 is 33. So, 23 into 1.085 microsecond is 25 microseconds. So, I have to load minus 23 in a decimal value, minus 23 has to be loaded with the TH0, so that I can generate 25 microseconds. So, you just see that I just made it T mod is 0x02, TH is 23 minus 23 and TR0 is equal to 1. I started the timer, loaded these two things, each and every time it gets an overflow, it gets loaded with minus 23 to TH TL0. So, each time when it gets a overflow, this TH0 which in turn loads minus 23 at TL0. So, I will be waiting till TF0 is equal to 1. When it is becoming 1, then I will be resetting TR0 and TF0. So that the delay of 25 millisecond is generated with this particular one, which has been called by 250 times into 36 times. So that I will be in a position to generate 250 millisecond delay with the timer mode 2. So, now you just see that this is in timer 1 and mode 2 to create a delay. So, this is also the similar kind of code where we will be doing it for different mode with the timer 1, that is all. So, when you are looking at a switch is connected to a pin 1.1, create a 8051C program to monitor the switch and create the following frequencies on the pin P1.7. So, if switch is equal to 0, then generate a 500 hertz signal. If switch is equal to 1, then generate 750 hertz signal. So, use timer 0 mode 1 for both of them. So, this is the specification they have given. So, now I made it S bit is equal to my bit P1.5. So, because I need to generate the values, you just see that yes, switch is connected to P1.2 and the frequencies should be generated at P1.7. So, I just made it S bit P1.7. Now, I will be looking at SW is equal to 1. So, my SW is nothing but P1.7 where I will be making that as the input where we will be giving the data over there. And while 1 my bit is inverted, that means I am just toggling it each and every time. This is to create clock cycle. If the switch is equal to 0, I will be calling one delay, which is time mode 1 delay 0, else call time mode 1 delay 1. That means if switch is equal to 0, I am calling a delay of 1 1. If it is equal to 1, else it comes over there and it calls this particular delay. So, which takes care about either 500 hertz is generated or 750 hertz is generated. You just see over here, if it is 500 hertz, then I need to generate one particular value. If it is equal to 750 hertz, I have to generate another delay. So now you just see that T mod is equal to 0x01. If C is equal to 0, I will be loading TL0 as 0x67, TH0 is equal to 0xFC. Else the value loaded is 0x9A, TH0 is equal to 0xFT. So if it is 1, I will be generating a 750. Just see that if it is 1, 750 hertz is generated. If it is 0, 500 hertz is generated. So if C is equal to 0, then this value is generated, which generates 500 hertz. If I am loading these two values, which in turn makes 750 megahertz, hertz clock cycle. So these are the values only we are changing it for generating the things. Otherwise it will be the similar one. TR0 is equal to 0, while TF0 is equal to 0, then till then it will be locked up. It has been made it on 1, the timer runs, the delay is generated. When it becomes an overflow, then these two are reset. So this is the way we will be generating two different clock cycles based with the same timer mode only, but we will be in the code we have changed the setting times in a different way, so that we will be in a position to generate two different frequencies at your output. So we know very well the timers can be used as a counters. So if I wanted to use as a counter, I have to set the gate bit as 1. So based on that only I can make it the timer should work as a counter. So if this is the case, the C bar T is equal to 1, and we will be counting the data which has been given from either T0 or T1. That is, the pin 14 means T0, which is nothing but P3.4, pin 15 is nothing but P3.5. This T0 and T1, which will be used as a counter, as counters external input. So if I am connecting the signals over here, I will be in a position to count how much is the occurrence happening. So just see that this picture explains you how the counter works. So the TR should be 1, and whatever be the data I wanted to get counted, that has been either connected to 3.4 or 3.5 of the 8051 port, and each time it gets the value from here, this gets incremented with the registers. When it gets overflow, this TF is set. So either it is in mode 1 or mode 2, we can use it. So when you are looking at the timer control register, we have to set TR0, we have to clear your TF0. So these are the things we have to look at. These are available in your TCON registers. So this is an example program to make it, the timer has to work as a counter 1. So counter. So here assume that a 1 hertz external clock is being fed in the pin T1, that means P3.5. Write a C program for counter 1 in mode 2. To count up and display the state of TL1 in TL1 on P1 port 1 and the count is started at 0. So this is the way we need to do it. Remember, it is a 1 hertz external clock. This has been given as P3.5. So now the counter has to be set with mode 2, so that we can find out. So S bit T1 P3.5, 3.5 the external pin. Now T1 is equal to 1, we made it, this becomes an input port. T mod is 0x60, timer 1 mode 2 and acts as a counter, has been set with this 60 with the T mod. TH1 is equal to 0, initial count is 0, we made it because it is mode 2, and while 1, that means indefinite loop is generated, do TR1 is equal to 0, P1 is equal to TL1. Each and every time I am getting an increment that will be displayed to my port 1. So that's what we want to continuously, we wanted to monitor what is the count, it has been increasing whenever I am getting a count over there. So now you just see that because we set these two values and we made it TR1 is equal to 1, so counter starts. So each time I am getting a signal at P3.5 which gets incremented, and this value is simultaneously displayed at your P1, while TF is equal to TF1 is equal to 0. So till then this goes in a loop. So when it becomes a 1, then it comes over here. So TR1 is made it as 0, TF1 is made it to 0 to clear the things. So remember that the timer is made it into counter. Each time it gets a input from external pin P3.5 is incrementing the TL1, not as the CPU clock cycle, and it has been available with your TL1. So, each and every time you can see that whatever be the value incremented which is displayed at P1 also. So, in this module we have discussed about timer programming, timer registers with embedded C, and we have discussed about counter concept in 8051, and we discussed about how to write embedded C counter programming as well as timer programming for different applications. So, all these things you can refer it with the Masdi book. Thank you.